A plasma display panel is a type of flat panel display common to large TV displays 30 inches or larger. They are called plasma displays because the technology utilizes small cells containing electrically charged ionized gases, or what are in essence chambers more commonly known as fluorescent lamps. General characteristics: plasma displays are bright, have a wide color gamut, and can be produced in fairly large sizes up to 3.8 meters diagonally. They had a very low luminance dark room black level compared with the lighter gray of the unilluminated parts of an LCD screen, at least in the early history of the competing technologies. LED backlit LCD televisions have been developed to reduce this distinction. The display panel itself is about 6 cm thick, generally allowing the device's total thickness to be less than 10 cm. Power consumption varies greatly with picture content, with bright scenes drawing significantly more power than darker ones. This is also true for CRTs as well as modern LCDs, where LED backlight brightness is adjusted dynamically. The plasma that illuminates the screen can reach a temperature of at least 1200 °C. Typical power consumption is 400 watts for a 127 cm screen. 200 to 310 watts for a 127 cm display when set to cinema mode. Most screens are set to shop mode by default, which draws at least twice the power of a home setting of less extreme brightness. Panasonic has greatly reduced power consumption. Panasonic states that PDPs will consume only half the power of their previous series of plasma sets to achieve the same overall brightness for a given display size. The lifetime of the latest generation of plasma displays is estimated at 100,000 hours of actual display time, or 27 years at 10 hours per day. This is the estimated time over which maximum picture brightness degrades to half the original value. This causes glare from reflected objects in the viewing area. Companies such as Panasonic coat their newer plasma screens with an anti-glare filter material. Currently, plasma panels cannot be economically manufactured in screen sizes smaller than 82 cm. Although a few companies have been able to make plasma-enhanced definition televisions this small, even fewer have made 32-inch plasma HD TVs. With the trend toward large-screen television technology, the 32-inch screen size is rapidly disappearing. Though considered bulky and thick compared with their LCD counterparts, some sets such as Panasonic's Z1 and Samsung's B860 series are as slim as 2.5 cm thick, making them comparable to LCDs in this respect. Competing display technologies include cathode ray tube, organic light emitting diode, AMLCD, digital light processing DLP, SED TV, LED display, field emission display, and quantum dot display. Plasma display advantages and disadvantages. Advantages: picture quality, capable of producing deeper blacks allowing for superior contrast ratio, wider viewing angles than those of LCD. Images do not suffer from degradation at high angles like LCDs, less visible motion blur, thanks in large part to very high refresh rates and a faster response time, contributing to superior performance when displaying content with significant amounts of rapid motion. Disadvantages: earlier generation displays were more susceptible to screen burn-in and image retention. Recent models have a pixel orbiter that moves the entire picture slower than is noticeable to the human eye, which reduces the effect of burn-in but does not prevent it. Due to the bistable nature of the color and intensity generating method, some people will notice that plasma displays have a shimmering or flickering effect with a number of hues, intensities and dither patterns. Earlier generation displays had phosphors that lost luminosity over time, resulting in gradual decline of absolute image brightness. Screen door effects become noticeable on screen sizes larger than 127 cm. The effect is more visible at shorter viewing distances. Uses more electrical power, on average, than an LCD TV. Does not work as well at high altitudes above 2 km due to pressure differential between the gases inside the screen and the air pressure at altitude. It may cause a buzzing noise. Manufacturers rate their screens to indicate the altitude parameters. For those who wish to listen to AM radio, or are amateur radio operators or shortwave listeners, The radio frequency interference from these devices can be irritating or disabling. Plasma displays are generally heavier than LCD, and may require more careful handling, such as being kept upright. Native plasma television resolutions. Fixed pixel displays such as plasma TVs scale the video image of each incoming signal to the native resolution of the display panel. The most common native resolutions for plasma display panels are 853A, 480, 1366A, 768 or 1920A, 1080. As a result, picture quality varies depending on the performance of the video scaling processor and the upscaling and downscaling algorithms used by each display manufacturer. Enhanced definition plasma television. Early plasma televisions were enhanced definition with a native resolution of 840A, 480 or 853A, 480, and downscale their incoming high-definition video signals to match their native display resolution. Idi Resolutions. Following Idi Resolutions were common prior to the introduction of HD displays, but have long been phased out in favor of HD displays. 840A, 480p, 853A, 480p, high-definition plasma television. Early high-definition plasma displays had a resolution of 1024x1024 and were alternate lighting of surfaces panels made by Fujitsu Hitachi. These were interlaced displays, with non-square pixels. Modern HD TV plasma televisions usually have a resolution of 1024A, 768 found on many 42-inch plasma screens, 1280A, 768, 1366A, 768 found on 50-in, 60-in, and 65-in plasma screens, or 1920A, 1080 found in plasma screen sizes from 42-inch to 103-inch. These displays are usually progressive displays, with square pixels, and will upscale their incoming standard definition signals to match their native display resolution. HD resolutions, 1024A, 1024, 1024A, 768, 1280A, 768, 1366A, 768, 1280A, 1080, 1920A, 1080. How plasma displays work. A panel typically comprises millions of tiny cells in between two panels of glass. These compartments, or bulbs, or cells, hold a mixture of noble gases and a minuscule amount of another gas. Just as in the fluorescent lamps over an office desk, when the mercury is vaporized at a temperature of over 1200 degrees Celsius and a high voltage is applied across the cell, the gas in the cells form a plasma. With flow of electricity, some of the electrons strike mercury particles as the electrons move through the plasma, momentarily increasing the energy level of the atom until the excess energy is shed. Mercury sheds the energy as ultraviolet photons. The UV photons then strike phosphor that is painted on the inside of the cell. When the UV photon strikes a phosphor molecule, it momentarily raises the energy level of an outer orbit electron in the phosphor molecule, moving the electron from a stable to an unstable state. The electron then sheds the excess energy as a photon at a lower energy level than UV light. The lower energy photons are mostly in the infrared range, but about 40% are in the visible light range. Thus the input energy is shed as mostly heat but also as visible light. Depending on the phosphors used, different colors of visible light can be achieved. Each pixel in a plasma display is made up of 3 cells comprising the primary colors of visible light. Varying the high voltage of the signals to the cells thus allows different perceived colors. The long electrodes are stripes of electrically conducting material that also lie between the glass plates, in front of and behind the cells. The address electrodes sit behind the cells, along the rear glass plate, and can be opaque. The transparent display electrodes are mounted in front of the cell, along the front glass plate. As can be seen in the illustration, the electrodes are covered by an insulating protective layer. Control circuitry charges the electrodes that cross paths at a cell, creating a voltage difference between front and back. Some of the atoms in the gas of a cell then lose electrons and become ionized, which creates an electrically conducting plasma of atoms, free electrons, and ions. The collisions of the flowing electrons in the plasma with the inert gas atoms leads to light emission. Such light-emitting plasmas are known as glow discharges. In a monochrome plasma panel, the gas is usually mostly neon, and the color is the characteristic orange of a neon-filled lamp. Once a glow discharge has been initiated in a cell, it can be maintained by applying a low-level voltage between all the horizontal and vertical electrodes even after the ionizing voltage is removed. To erase a cell, all voltage is removed from a pair of electrodes. This type of panel has inherent memory. A small amount of nitrogen is added to the neon to increase hysteresis. In color panels, the back of each cell is coated with a phosphor. The ultraviolet photons emitted by the plasma excite these phosphors, which give off visible light with colors determined by the phosphor materials. This aspect is comparable to fluorescent lamps and to the neon signs that use colored phosphors. Every pixel is made up of 3 separate subpixel cells, each with different colored phosphors. One subpixel has a red light phosphor, one subpixel has a green light phosphor, and one subpixel has a blue light phosphor. These colors blend together to create the overall color of the pixel, the same as a triad of a shadow mask CRT or color LCD. Plasma panels use pulse width modulation to control brightness. By varying the pulses of current flowing through the different cells thousands of times per second, the control system can increase or decrease the intensity of each subpixel color to create billions of different combinations of red, green and blue. In this way, the control system can produce most of the visible colors. Plasma displays use the same phosphors as CRTs, which accounts for the extremely accurate color reproduction when viewing television or computer video images. Plasma displays should not be confused with liquid crystal displays, another lightweight flat-screen display using very different technology. LCDs may use 1 or 2 large fluorescent lamps as a backlight source, but the different colors are controlled by LCD units, which in effect behave as gates that allow or block the passage of light from the backlight to red, green, or blue paint on the front of the LCD panel. Contrast ratio. Contrast ratio is the difference between the brightest and darkest parts of an image, measured in discrete steps, at any given moment. Generally, the higher the contrast ratio, the more realistic the image is. Contrast ratios for plasma displays are often advertised as high as 5,000,000. On the surface, this is a significant advantage of plasma over most other current display technologies, a notable exception being organic light-emitting diode. Although there are no industry-wide guidelines for reporting contrast ratio, most manufacturers follow either the ANSI standard or perform a full-on full-off test. The ANSI standard uses a checkered test pattern whereby the darkest blacks and the lightest whites are simultaneously measured, yielding the most accurate real-world ratings. In contrast, a full-on full-off test measures the ratio using a pure black screen and a pure white screen, which gives higher values but does not represent a typical viewing scenario. Some displays, using many different technologies, have some leakage of light, through either optical or electronic means, from lit pixels to adjacent pixels so that dark pixels that are near bright ones appear less dark than they do during a full-off display. Manufacturers can further artificially improve the reported contrast ratio by increasing the contrast and brightness settings to achieve the highest test values. However, a contrast ratio generated by this method is misleading, as content would be essentially unwatchable at such settings. Plasma is often cited as having better black levels, although both plasma and LCD each have their own technological challenges. Each cell on a plasma display has to be pre-charged before it is due to be illuminated, and this pre-charging means the cells cannot achieve a true black, whereas an LED backlit LCD panel can actually turn off parts of the screen. Some manufacturers have worked hard to reduce the pre-charge and the associated background glow, to the point where black levels on modern plasmas are starting to rival CRT. With LCD technology, black pixels are generated by a light polarization method. Many panels are unable to completely block the underlying backlight. However, more recent LCD panels can compensate by automatically reducing the backlighting on darker scenes, though this method analogous to the strategy of noise reduction on analog audio tape obviously cannot be used in high-contrast scenes, leaving some light showing from black parts of an image with bright parts, such as a solid black screen with one fine intense bright line. This is called a halo effect, which has been almost completely minimized on newer LED backlit LCDs with local dimming. Edge-lit models cannot compete with this as the light is reflected via a light funnel to distribute the light behind the panel. Screen burn-in. Image burn-in occurs on CRTs and plasma panels when the same picture is displayed for long periods. This causes the phosphors to overheat, losing some of their luminosity and producing a shadow image that is visible with the power off. Burn-in is especially a problem on plasma panels because they run hotter than CRTs. Early plasma televisions were plagued by burn-in, making it impossible to use video games or anything else that displayed static images. Plasma displays also exhibit another image retention issue, which is sometimes confused with screen burn-in damage. In this mode, when a group of pixels are run at high brightness for an extended period, a charge buildup in the pixel structure occurs and a ghost image can be seen. However, unlike burn-in, this charge buildup is transient and self-corrects after the image condition that caused the effect has been removed and a long enough period has passed. Plasma manufacturers have tried various ways of reducing burn-in, such as using gray pillar boxes, pixel orbiters and image washing routines, but none to date have eliminated the problem, and all plasma manufacturers continue to exclude burn-in from their warranties. Environmental impact. Plasma screens have been lagging behind CRT and LCD screens in terms of energy consumption efficiency. To reduce the energy consumption, new technologies are also being found. Although it can be expected that plasma screens will continue to become more energy efficient in the future, a growing problem is that people tend to keep their old TVs running and an increasing trend escalating screen sizes. History. In 1936, Kálmán Sándor, a Hungarian engineer, described the principle of plasma television, and conceived the first flat-panel display system. The monochrome plasma video display was co-invented in 1964 at the University of Illinois at Urbana-Champaign by Donald Bitter, H. Gene Slotto, and graduate student Robert Wilson for the Plato computer system. The original neon-orange monochrome DigiView display panels built by glass producer Owens, Illinois were very popular in the early 1970s because they were rugged and needed neither memory nor circuitry to refresh the images. A long period of sales decline occurred in the late 1970s because semiconductor memory made CRT displays cheaper than the $2,500 512x512 Plato plasma displays. Nonetheless, the plasma display's relatively large screen size and 1-inch thickness made them suitable for high-profile placement in lobbies and stock exchanges. Burroughs Corporation, a maker of adding machines and computers, developed the Panaplex display in the early 1970s. The Panaplex display, generically referred to as a gas discharge or gas plasma display, uses the same technology as later plasma video displays, but began life as 7-segment display for use in adding machines. They became popular for their bright orange luminous look and found nearly ubiquitous use in cash registers, calculators, pinball machines, aircraft avionics such as radios, navigational instruments, and stormscopes. Test equipment such as frequency counters and multimeters. And generally anything that previously used Nixie tube or Numatron displays with a high digit count throughout the late 1970s and into the 1990s. These displays remained popular until LEDs gained popularity because of their low current draw and module flexibility, but are still found in some applications where their high brightness is desired, such as pinball machines and avionics. Pinball displays started with 6- and 7-digit 7-segment displays and later evolved into 16-segment alphanumeric displays, and later into 128x32 dot matrix displays in 1990, which are still used today. 1983 In 1983, IBM introduced a 19 inches orange on black monochrome display which was able to show up to 4 simultaneous IBM 3270 terminal sessions. Due to heavy competition from monochrome LCDs, In 1987 IBM planned to shut down its factory in upstate New York, the largest plasma plant in the world, in favor of manufacturing mainframe computers. Consequently, Larry Weber co-founded a startup company Plasmarco with Stephen Globus, as well as James Keogh, who was the IBM plant manager, and bought the plant from IBM. Weber stayed in Urbana as CTO until 1990, then moved to upstate New York to work at Plasmarco. 1990s, 1992. In 1992, Fujitsu introduced the world's first 21-inch full-color display. It was a hybrid, the plasma display created at the University of Illinois at Urbana-Champaign and NHK Science and Technology Research Laboratories, 1994. In 1994, Weber demonstrated color plasma technology at an industry convention in San Jose. Panasonic Corporation began a joint development project with Plasmarco, which led in 1996 to the purchase of Plasmarco, its color AC technology, and its American factory. 1995. In 1995, Fujitsu introduced the first 42-inch plasma display. It had 852x480 resolution and was progressively scanned. Also in 1997, Philips introduced a 42-inch display, with 852x480 resolution. It was the only plasma to be displayed to the retail public in 4 Sears locations in the U.S. The price was $14,999 and included in-home installation. Later in 1997, Pioneer started selling their first plasma television to the public, and others followed. 2000s, 2006 Euro 2009. In late 2006, analysts noted that LCDs overtook plasmas, particularly in the 40-inch and above segment where plasma had previously gained market share. Another industry trend is the consolidation of manufacturers of plasma displays, with around 50 brands available but only 5 manufacturers. In the first quarter of 2008, a comparison of worldwide TV sales breaks down to $22.1 million for direct view CRT, $21.1 million for LCD, $2.8 million for plasma, and $0.1 million for rear projection. Until the early 2000s, plasma displays were the most popular choice for HD TV flat panel display as they had many benefits over LCDs. Beyond plasma's deeper blacks, increased contrast, faster response time, greater color spectrum, and wider viewing angle. They were also much bigger than LCDs, and it was believed that LCD technology was suited only to smaller-sized televisions. However, improvements in VLSI fabrication technology have since narrowed the technological gap. The increased size, lower weight, falling prices, and often lower electrical power consumption of LCDs now make them competitive with plasma television sets. Screen sizes have increased since the introduction of plasma displays. The largest plasma video display in the world at the 2008 Consumer Electronics Show in Las Vegas, Nevada, was a 150 inches unit manufactured by Matsushita Electric Industrial standing 6 ft tall by 11 ft wide. 2010s, at the 2010 Consumer Electronics Show in Las Vegas, Panasonic introduced their 152 inches 2160p 3D plasma. In 2010 Panasonic shipped 19.1 million plasma TV panels. In 2010, the shipments of plasma TVs reached 18.2 million units globally. 2013, in late 2013, Panasonic announced that they will stop producing plasma TVs from March 2014 onwards. 2014, on July 2, 2014, Samsung announced that they will stop producing plasma TVs from November 2014 onwards. Notable plasma display manufacturers: Panasonic, Pioneer, Samsung, LG, Toshiba, Gradient, Lanix, ProScan, Sanyo, Funai, Magnavox. See also, display examples, large screen television technology, list of plasma articles, references. External links: plasmatrfscience.org The plasma behind the plasma TV screen, archive.org Plasma display panels, The Colorful History of an Illinois Technology by Jamie Hutchinson, Electrical and Computer Engineering Alumni News, Winter 2002 Euro 2003, Nighttimes.com Euro Figured LCD. Go for Plasma, says maker of both according to Panasonic Corporation. Home Theatre Geeks Euro 13, Plasma Geek Out, Plasma 1080p.net Euro Plasma 1080p Information and Resources.